In completing the table, for pattern 1, we started with 1 dot, and then every time we added 2. So this would be 3, adding 2 gives us 5, 7, adding 2 again would give us 9, and then 11. However, we notice the step number goes 0, 1, 2, 3, 4, 5, then it skips to 10. So we're better off right here using our equation. So if we say that y is the number of dots, we could just use our equation 2 times the step number plus 1. So in this situation, we can go 2 times 10 plus 1. 2 times 10 is 20, plus 1 gives us 21. Now, the other step number we saw was just a square. So if the square is n, we would say it's n squared, which equals n times n. So in evaluating this, step 0 would be 0 to the second power, which expands to 0 times 0, which is 0. Step 1, 1 squared, that expands to 1 times 1, which is 1. Step 2 is 2 squared, which is 2 times 2, which gives us 4. Step 3, 3 to the second power, that means 3 times 3, which is 9. Step 4, 4 squared, that's 4 times 4, which is 16. Step 5 is 5 to the second power, which gives us 5 times 5, which is 25. And then we skip to step 10, which is 10 to the second power, or 10 times 10, which gives us 100. So now we go back and plot our graphs. So we're going to start with pattern 1. Now for step 0, we're at 1. So I plot right there. Then I remember for step 1, I add 2, so 1 plus 2 is 3. I estimate about there. For step 2, we were at 3. We add 2, so that brings us to 5. For step 3, I start at 5, add 2, and bring us to 7, so I estimate that to be about right there. For step 4, I'm at 7, add 2, that is about 9. For step 5, at 9, I go to about 11. And then for step 6, I'm at about 13. So you can see a linear pattern here. And then we will skip to graphing pattern 2. Now this was actually very different. This is a new pattern. We're actually going to learn that this is called quadratic. But here, step 0, 0 squared is 0. Step 1, 1 times 1 is 1. Step 2, we go 2 to the second power, 2 times 2 is 4. Step 3, 3 to the second power, 3 times 3 is 9. Step 4, 4 to the second power, 4 times 4 is 16. Step 5, 5 to the second power, 5 times 5 is 25. And then step 6 would actually be off the graph. So if I were to connect these dots, we can see 1, this is nonlinear, and that we actually see an increasing slope. So in explaining why the two patterns look the way they do, we could say pattern 1 is linear. And then examining pattern 2, we see that when we multiply the variable times itself or square it, it's called quadratic and it's not linear. So now we're going to look at some more growth patterns. And we need to examine this growth pattern and look at the number of squares. So in step 1, I notice there's 3 squares. In step 2, there's 6. In step 3, if I count them, I notice in the middle there's a 3 by 3 square, which is 9, and then 2 on the ends, which adds 2 to the 9 and makes 11. So in examining the change in the number of squares, I add 3, and then from 6 to 11, I add 5. And then this for sure is nonlinear because I'm not adding 3 each time. But again, we don't know that if this is quadratic for sure yet. So as we examine the rate of change, I notice I add 3 and then I add 5. I might think that for the next one I add 7, and then if I go from 11 to 7, that gives us 18. So I might think that in step 4, we have 18, but I'm not sure. So I'm going to examine this and look for a number pattern. Now, it's hard for me to see a pattern in step 1, but in step 2, I definitely see a 2 by 2 square, which would give me 2 to the 2nd power, and then I have 2 squares on the end, so then I add 2. In step 3, I see a 3 by 3 square, which is 3 to the 2nd power, and then I add 2. So I think for step 4, I would have a 4 by 4 square, or 4 squared, and then 2 on the ends. Checking that, 4 squared is 16, plus 2 gives me 18. So let me just confirm that with a picture. So I would have a 4 by 4 square, and if I count those, that gives me 16 plus 2 is 18 for sure. So if I go down here, I came up with a general pattern. If it's n, we have n squared, and then I add 2. So using that formula for 5, we would have 5 squared plus 2. That's 25 plus 2, which is 27. If I had 10 for my step number, it would be 10 to the 2nd power plus 2. 10 squared is 10 times 10, which is 100, plus 2 is 102. And then 12, we have 12 squared plus 2. 12 to the 2nd power, 144, plus 2 is 146. So is the number of squares growing exponentially? No, I'm not constantly multiplying by the same number. It's quadratic because we're squaring a number. So in the summary, we see that the relationship between the step number and the number of squares is quadratic if you multiply the variable by itself. Okay, ladies and gentlemen, so this is Unit 4, Lesson 2. It's called How Does It Change? So we're looking at little different patterns and patterns of dots here. So as we look at the 2 patterns, we see this pattern in step 0, there's 1 dot. Step 1, if we count the dots, there's 3. Step 2, if we count the dots, there's 5. Step 3, if we count the dots, there's 7. So in looking at this, we can see I start with 1 dot, and then in the first step, I have 3 dots. In the second step, I have 5 dots, and in the third step, I have 7 dots. In examining this, we could see that we are constantly adding 2, or that the slope of this relationship between step number and number of dots is 2, or the rate of change is 2, and this is in fact linear. For step 2, for pattern 2, this actually looks very different. So if we're looking here at the step number and the number of dots we see for step 0, there's 0. For step 1, there's 1. For step 2, there's 4. For step 3, there's 9. And this is just a very different relationship. So as I examine the shape of the pattern, I see a big shape in steps 2 and step 3. I notice step 2 is a 2 by 2 square, step 3 is a 3 by 3 square, and then I notice step 0, I could think of that as a 1 by 1 square, and this is a 0 by 0 square. So here, if I'm now examining how the patterns are changing, for pattern 1, I could say I start with 1 dot and add 2 dots for each step. Whereas in pattern 2, I see that if I wanted the number of dots, I could just take the step number and multiply it by the step number. So how would you find the number of dots in the 5th step of each pattern? Well, in the first part of algebra, we learned how to write an equation. So for this equation, for this pattern, I notice that this is linear. So if I did y for my output, I see that my y-intercept, or at step 0, is going to be 1. So we could say 1 plus my rate of change is 2. So I could say that's 1 plus 2 times x, or 2 times the step number. So for the 5th step, we could plug in 5 and say that's going to be y equals 1 plus 2 times 5. And then evaluating that, that's 1 plus 10, which is 11. For this new pattern of change, we could say that y, the number of dots, equals the step number, which we'll just call x in this case, times x, or we can say that's x to the 2nd power. So if we want to step 5, we would simply say 5 squared, which is 5 times 5, would give us 25 dots.